Sampling techniques and the uses of sampling techniques. So in inferential statistics, the logic is we take a sample out of a population of interest, we study the sample, we can make inferences about the population, assuming that the sample is random. This is very important to distinguish because if the sample is not random, then we can only make inferences about the sample. So what is data sampling? It is a statistical data collection technique that is used to determine how much data we must collect, and this is referred to as the sample size, and how often a sample should be taken from the population of interest, and this is referred to as the sampling frequency. It helps define the samples to take in order to quantify a system, a process, an issue, or a problem. More specifically, a business problem, which is the focus of Lean Six Sigma projects. Data sampling is the collection of statistical samples from the population, followed by the analysis that will help us estimate the characteristics of interest of the population, the parameters of interest, from sample statistics. This technique is helping to make statistical inferences from the statistic to the parameter. We have different types of data sampling. So when we're taking a sample from a larger population, you must make sure that the samples are an appropriate size and there is no bias. You should address these concerns if your data is biased or otherwise in your data collection plan. And you may remember that this is something that we create at the beginning of the measure phase of DMAIC. So we start with a list of research questions, the answers of which will help us to solve a business problem. Based on the research questions, we create the data collection plan, and this specifies which type of data we must collect, how frequently, what will be the sample size, who is going to collect the data, how the data is to be collected, etc. So there are two broad categories of data sampling: probability sampling and non-probability sampling. And in our course, we're focusing in the first type, in probability sampling. So, every element in the sample population has an equal chance of being selected. This is what we call random sampling. So a sampling method is biased if every member of the population does not have an equal chance or likelihood of being selected and becoming part of the sample. We have four types of probability sampling: simple random sampling, stratified sampling, systematic sampling, and cluster sampling. So simple random sampling, that's a method of sampling in which every element of the population of interest, of the universe of interest, has equal probability of being chosen. So in the figure, you can see a population that has apples of different colors, and you can see how a random sample looks like. Stratified sampling is a method in which the population is broken down into non-overlapping groups. And these groups are known as strata. Strata are homogeneous or heterogeneous elements within the subgroups, and random samples are taken from each strata so that the entire population is represented. And again, we have an example in the figure where out of the population strata, we take out a stratified sampling. So, systematic sampling. This is a method in which samples are selected from the population according to a predetermined rule. For example, every ninth, like every fifth element, is selected for the population as sample. All the elements are arranged in a sequence, and then the samples are collected from the population at irregular intervals. And again, you can see in the sample the population of red apples, and you can see the sample where, for example, we pick up every third apple in the sequence. And finally, cluster sampling. That's a method in which the population is broken down into many different clusters, and then clusters or subgroups are randomly selected. Again, in the figure, we can see an example of the population broken down into many different clusters, and then we can see how the sample looks like. So the question is, when should we use data sampling? And the sampling technique should be used at any time when data must be collected for statistical analysis purposes. Data collection can start after the sample size and the sampling frequency have been determined and recorded in the data collection plan, which is created during the measure phase of DMAIC. Two questions, how much and how often, are at the heart of data collection sampling. So when data is collected on a regular basis in order to monitor the behavior of a specific system or a specific business process, the sample size and the sampling frequency should be periodically reviewed. And if both are still appropriate, they should continue to be used as before, or we may need to make some minor adjustments based on what we have learned from data collection up to a specific point in time. Why should we use data sampling? That's a very fair question. Sometimes collecting data on the entire population of interest may be too time-consuming, too expensive, or both. For example, we may take samples when the process we're measuring would require destructive testing, just like, car crash tests, etc. Collecting data from the entire population is too expensive. It would take much longer than the available time that we have. Remember, during the measure phase of DMAIC, the project manager and the project team, they have specific length of time during which they may have to complete, the measure phase. Now, if you consider that data collection and data sampling, is only a fraction of the measure phase of DMAIC, then you have to take into consideration and calculate accordingly what is the correct sample size and what is the appropriate sampling frequency that you have to employ. Let's get into specifics about the sample size. This is a topic that we touched upon during the Lean Six Sigma Yellow Belt training, but it is very appropriate at this point in order to revisit the topic again. So the two core elements of data sampling are sample size, how much data to collect, and the sampling frequency, how frequently should we collect a sample. Sample size refers to the number of elements or observations included in a study. And typically this number is represented by the lowercase letter n. The sample size influences two statistical properties. The first one is the precision of our estimates, and the second is the power of the study in order to draw statistically valid conclusions based on analyzing and studying the sample. Here, on this figure, we have an example of a statistical table that we can use in order to determine what is the statistically correct sample size. If you look on the left-hand column, you can see that the population size is covered in a pretty wide range, starting with less than 100 and going all the way up to 300 million. So the population size is one component that we have to take into consideration when we're thinking about what is the statistically correct sample size. The other one is the margin of error that is acceptable, and we're going to talk shortly about the margin of error. Typically, commercially, it is acceptable to assume that if we have a confidence level of 95% about the statistical outcome of an experiment, this allows for a 5% margin of error. So this is typically what is commercially acceptable. As we're going to learn when we talk about hypothesis testing, this corresponds to one type 1 error out of 20 statistical tests. So this is what is considered as acceptable. So based on the size of the population of interest and the margin of error, at the intersection on the statistical table, we can find what is the statistically correct sample size. And a very fair question is, do we always have the time and the resources to collect the statistically correct sample size? And the practical answer is, it depends. If you have sufficient time and resources, then the statistically correct sample size provides a good balance between risk, margin of error, and accuracy of your statistical analysis. If you don't have sufficient time and resources to collect a statistically correct sample size, for example, of 500, then you collect whatever you can practically do. It may be 50 instead of 500. However, the larger the difference between statistically correct and what you actually collect, the less accurate your conclusions and your predictions from the data analysis will be. So that's the practical knock-on effect. Another way in order to calculate what is the statistically correct sample size is to use online sample size calculators. And again, you have one example on the figure where, based on the data that you input, what is the margin of error, what is the confidence level, etc. You can see that the statistically correct sample size in this particular example is 385. And of course, there's always the possibility that you can use a mathematical formula in order to calculate the sample size, but this is rather cumbersome. So what is recommended is consider either an online sample size calculator or a statistical table to determine it. There are three very important terms when we refer to quantifying the sampling error. SE, which stands for standard error, MOE, margin of error, and CI for confidence interval. So we'll start with the standard error. This is the standard deviation of the means. It quantifies the variation in the means from various sets of measurements data, and it is a measure of uncertainty in the sample mean. If the sample size increases, the standard error decreases. Margin of error in statistics is expressing the amount of random sampling error in the results of an experiment. And finally, a very important term, a confidence interval. So I mentioned earlier that in inferential statistics, we take a random sample from a population of interest, we study the sample, we calculate the statistic of interest, and from the statistic of interest, we make inferences about a population parameter. Now, when we refer to the confidence interval, this is typically a range around a measurement that conveys how precise the measurement is. In other words, many statistical software packages like Minitab, they calculate the confidence interval. And this is a range within which we would expect the population parameter to fall if everything has been done correctly in our calculations. Because it is virtually very, very rare, if not impossible, that the statistic of interest associated with the sample corresponds precisely with the population parameter. There is always a difference between them. That's why we refer to the confidence interval as a range between value X and value Y, that we hope it will contain the population parameter. You can see in the figure the one about the confidence interval. So we see that we have the estimate, and the estimate corresponds to the statistic of interest associated with the sample, and depending on with what is the acceptable margin of error, this determines the width of the confidence interval. And again, we have another example of a statistical calculator that we can find online, and it estimates the margin of error. In this case, we have placed the figure of 361, and the margin of error is 158.